In our first lesson for organic chemistry, we need to start by learning how to name organic compounds. Organic compounds are really any compound that is based around the carbon atom, and they can vary extremely large amounts in complexity. Now, carbon is very versatile because it's able to make these 4 bonds per atom. What that means is I've got drawn up here 3 carbon chains. These 3 carbon chains, theoretically, don't have to stop where I've stopped them. I could easily erase any one of these hydrogens and just continue drawing carbons, seemingly for eternity. It could just keep linking onto itself. So we need a comprehensive naming structure in order to keep track of how many carbons are in this. What would I name this? Tricarbon octahydrogen? That's going to get a little long if I've got 20 carbons, as I can sometimes have, and it doesn't inform me anything about if I've got a double bond, or let alone if my carbons circle around each other and form a ring. I need a specific naming structure in order to identify which molecules I'm working with. Now, back in the day for organic compounds, we just named them by whatever was convenient. The scent of lemons? Limonene. The scent of cinnamon? Cinnamaldehyde. Sounds great. However, these don't inform us about their structure at all. And so the IUPAC came in and developed a straightforward, comprehensive naming system. The IUPAC stands for the International Union of Practical and Applied, or not practical, Pure and Applied Chemistry. It's a mouthful. IUPAC is much easier to say, and we'll probably never say it again after this. But they've defined a nomenclature for how we are able to name and draw these compounds. That makes it very straightforward to communicate with anyone else in the world studying chemistry. I could email someone in China saying, I am working with this compound, 2-butyl-hexene, and they would know exactly what I'm talking about. Before we can get into naming, though, we need to simplify our drawings here. In regular chemistry, in general chemistry, we use Lewis dot structures in order to examine how our atoms might fit together. For something like C3H8, this would be my Lewis structure. Nice and straightforward. For C4H10, this would be it. Notice that for each carbon, where it terminates, where it's not connecting to anything else, it ends in a hydrogen. In organic chemistry, this is the first thing we can do to simplify these drawings, is that since everything is based around carbon, and since anytime carbon isn't attached to anything special, it will attach to a hydrogen, we can assume that unless something else is noted, it's attached to a hydrogen. Every carbon that we draw will be saturated with a hydrogen, unless it is identified otherwise. So unless I have something like a C to an O, I'm going to assume that there is a hydrogen hanging out right there. So if I don't have anything drawn, I should have a hydrogen. So I'm going to redraw these by just removing the hydrogens. That'll make my drawing a little bit simpler. So I've got C to C to C. Now all of my hydrogens are implied. I don't have to draw them. Anyone studying organic chemistry would know, well, of course, it's not attached to anything else that's special. It must be attached to a hydrogen. So we can imply our hydrogens. We don't need to draw them. Now further, in order to further simplify things, since every compound that we study is going to be based around carbon, it's going to have a bunch of carbon atoms in them, we could shorten our notation to imply that as well. The way we do that is by using a skeletal structure to draw our compounds. When we draw a skeletal structure, we identify each carbon as simply a point. It's just a point. So I've got a dot here, and then I'm going to draw my second carbon here. I'm going to draw my third carbon here. And then I'm just going to connect those lines. There we go. Now once you start drawing these and getting good at this, don't even worry about drawing the dots. For example, I've got 4 carbons here. I'm going to have 4 points and a line connecting each point. Each line is going to represent those bonds. So I start at my first carbon, then my second, third, fourth. There is my skeletal structure for C4H10. Much simpler, right? But what about that double bond here? How do I draw in that nasty little double bond? Well, it's going to be very simple. I'm just going to draw it just like I did up here. 3 points for 3 carbons, and then where I have that double bond, I'm going to draw a second line. And now that tells me I've got a double bond between my first and my second carbon. Okay? Now we can get into naming these. Once we're able to draw these in a skeletal structure, all we really need to know is how many carbons are there. Since everything else is going to be saturated with hydrogens, all I need to know to start with for naming a carbon chain is how many carbons. Okay? So let's look at how we name these. I have written over here the specific naming structure for these molecules. The first thing we need to identify is the number of carbons that are in the chain. The simplest one being a 1-carbon chain. That would just be C connected to as many hydrogens as it can. Carbon can make 4 bonds. It's going to be 4 hydrogens. So we would have methane being CH4. That's our simplest one. But the ones we were working with, I started with a 3-carbon chain. That was my 3-carbon chain. That was C3H8. How would I name that? Well, quite simply, I'm just going to count my number of carbons. 1, 2, 3. That would be prop. That would be my prefix, prop. So this will be prop, and then I need a suffix. I need to end this word with something. In order to do that, I just look at the types of bonds in my carbon chain. I only have single bonds, so I'm going to end it with an ane. So propane. Okay? Next, let's look at our C4H10. The skeletal structure for that was just like this. Now my C4, that's going to be 4 carbons. So my number of carbons is 4. I go over here, and that's bute. B-U-T. And then I don't have any double bonds. I only have single bonds. It's going to be butane. Butane. Okay. Finally, I've got my one that had a double bond. So I've got a drawing like this. That double bond there. I've got 1, 2, 3 carbons, so it's still going to be prop. But now I've got a double bond, so instead of ane, I put ene. So propene. When we're working with carbon chains, whatever our length of chain, if it's just a simple chain, we have a name to differentiate that from something else, from different types of organic molecules. Because a simple carbon chain is often simply used as a fuel source. It combusts and releases a lot of heat, and it has various other uses in reactions, but as far as practical uses, those are the primary functions that we use them for. These are often familiar terms to us. Methane is natural gas. If you have a natural gas water heater or furnace in your home, it runs on methane. If I get a grill and attach a tank to it, I usually have a propane tank, which would be C3H8. These carbon chains are called alkanes. So alkanes, if they have single bonds. If they're double bonded, they are known as alkenes, and a triple bond is alkyne. So there's our single, double, triple bonds. We will be comparing and contrasting these with other types of organic molecules, like aldehydes and esters, things like that. But for now, these are our basic rules.